All right, here we are almost at the finish line for laser bikes. In this video, what we're going to do is get the bike drawing the wall as opposed to us going in there and, well, manually creating one because that's no fun. And then we're going to make sure that wall collision detection is in place. And finally, we're going to get that smooth interpolation down so that when the bikes move around the level, they don't look, blocky, if you will. Okay?
All right, well, the first thing we'll do is wipe out our hard-coded wall. We don't need that anymore. We're about to make the bike set the wall. Cleaning up the create scene method just a little bit. Now we can turn our attention to the bike class. The first thing we need to do is set up the bike so that it knows how to set grid blocks as it passes over them. This will be done inside of the move method, which means that move is about to get a lot more interesting. And the first thing that we'll do in move is we'll take the position, which is a vector 2, two float components, and we'll cast those to integer variables for more convenient checking. So right below position, I'm going to make two integer variables. The first one will be x, and it will be the int casted result of, well, parenthesis would help, the int casted result of this dot position dot x.
Okay.
And we'll do the same thing for a variable called y, looking at the y component. Now with these convenient x and y variables, we can do a check to make sure that the bike's position is currently on the grid. This is very important because we're about to be addressing the wall segments array, and if we try to plug in a value that's not within its bounds, we will get an out-of-bounds exception.
Exactly.
So the very first thing we do here before we attempt to address the array is make sure we are within bounds. And so that means we need to make sure that x is greater than -1, and that y is also greater than -1, and that x is less than the grid width, so game1.grid width, and finally that y is less than the grid height.
Okay.
If all of these criteria are met, we are within bounds for the wall segments grid array. So the next thing we need to look at is remembering that we have passed over this grid segment. That means we need to remember that the grid segment is now filled and set its player index to an appropriate player index. So let's look at the wall, access its segments array, look up an address by x and y for the dimensions, and set the filled property to true, which is lowercase, and set the wall segments x by y dot player index to be equal to our player index for this bike. So this dot player index. Now the next thing we need to do is to decide what texture to save into this wall segment. And that gets a little bit more complicated because the texture we use is dependent on what direction we're going and whether or not we have just rounded a corner. Have we just turned? So that's going to be the next check. We need to detect if we have just turned or not. And notice I have moved the acknowledgement of the direction to the desired direction down. As a matter of fact, it'll have to be moved again, but it's important that this has not happened yet. It is important that this dot direction could potentially be different than the desired direction.
That's right.
Because that's what we're actually going to check
Meaning
right here.
we're interested in making a turn from the direction we're currently going.
Right. So we'll look at the direction, and we'll see if it is different than the desired direction. If it is, then we are attempting or about to round a corner. And also, let me move this line so that it doesn't get forgotten, since it is still very critical in the operation of the code here. I'll move that inside this if block, because if the direction is different, that's the only real case where we would need to sync it up later. Now, before we sync up the direction, let's take that difference and decide which corner wall segment to place. And this is going to simply include several compound checks to see if we've rounded a corner in one direction, clockwise or counterclockwise. So let's look at the first possible set of directions. As a matter of fact, I'm going to try to arrange these so that we look at potential elements 2 through 5. That is the top left corner to the top right, then bottom right, then bottom left. So again, going clockwise. Now, this should become more clear as we get some of these numbers put in place. So we'll begin an if statement. We'll check the current direction. And we'll see if the current direction is equal to direction dot left. So ours is our current direction left, and is our desired direction in the down direction. So is the desired direction equal to direction dot down? So what this means is if we are currently traveling left and we are about to be traveling down,
let me show this on the whiteboard if you don't mind.
What corner would draw us? Yeah, that's actually a good idea.
So basically, remember this over here when we were dealing with all of this earlier. So basically what Logan's saying is if we're currently moving, find a place to draw, left, and we want to move down, so we're moving left, we want to move down.
What corner block appropriately joins those two?
What corner block would be right. Now, as Logan goes through and creates all of these different if statements for each of the corners, there's two related scenarios where we'll use that particular corner block. Basically, like in this particular case, we're going left and we want to go down. There is an inverse of that. What if we were going up and wanted to go right? That would be the exact same corner piece that we'd want to use. So Logan's going to start in the upper left-hand corner. Like he said, he's basically done a great job with making everything deal with the upper left-hand corner and then going in a clockwise fashion dealing with each of the corners. So after he checks this, then the next one's going to be, are we going to the right and desired to go down, or are we going up with the desire to go to the left? And then that'll be the second check that you'll see. But basically what's going to happen, he's going to do this all the way around, and that'll cover all of our corner pieces.
All right, so jumping back to the code.
So now that you've got left and down, you're going to need to put an OR in there and check the inverse.
All right, so the inverse would be if we were currently moving up and wanted to move right.
Right.
So if this dot...
I meant to say that's right, not right. But
exactly.
Right is right.
I was running into that same thing earlier when we were talking about the D-pad. If you want to move in the right direction, that is to say not the correct direction, but if the current direction is up, and I don't know how D became a letter U, but direction dot up, and our desired direction is equal to the direction to the right, and then that would be the same corner piece, which means we want to set the wall segments sub x by y, the current wall segment. We want to set its texture index equal to 2.
Which makes sense because 0 was horizontal, 1 was vertical, then 2 starts the upper left-hand corner.
So visual reference right there. 0, 1, horizontal, vertical, 2 starts top left.
Exactly.
All right, so all that looks well and good. Let me copy the entire if statement and paste it 3 additional times. And let me also space that out just a little bit.
Throw a bunch of else's in.
Throw some else's.
Change all your 2's to 3, 4, and 5.
So 3, 4, and 5. Well, knowing that we're now looking for 3, which is the top right, what conditions would satisfy that?
We were going right and desired to turn down.
And that would be 1, so going from right to the direction down.
Or if we were going up and desired to turn left.
So if we're going up and desired to turn left, that would be the top right corner.
Okay. So now the bottom right would be if we were traveling to the right and desired to turn up, or if we were traveling down and desired to turn left. And then finally, the bottom left corner would be if we were traveling to the left, so this would be on the bottom leg, with the desired direction of going up, or if we were traveling down with the desired direction of going to the right, the inverse of it. And that would be 5. And there you go.
So those are the possible corners we could run into. After we choose one of those, then we'll make sure we set the direction to the desired direction. And then that should take care of all of the possible corners.
Okay.
Now, what happens if the direction was the same as the desired direction? Well, that simply means we haven't tried to change direction. We've been moving in a straight line. So that means I need to put an else into the overall if statement here. So if we had not just rounded a corner, we instead need to decide if we are moving horizontally or moving vertically. So this if check would just be looking at our own direction. So if this dot direction, now here's the interesting thing. We want to say we're first looking for the horizontal direction. So what satisfies that?
Well,
that
X.
would be x being equal to 1 or -1.
That's right.
Here it doesn't matter which direction. And so to make this check easier, what I'll do is I'll get the absolute value of x. So that way I can see if it's...
Or you could say if x is not equal to 0.
Or I could do that.
That'll just save you from having to call on...
I think I was originally doing that, or avoiding that, because of the vector being float, but since we're setting it directly, we could just say if direction is not equal to... direction.x is not equal to 0. That would be one possible way to do it.
Which means we're obviously going left or we're obviously going right. We can't be going diagonally, so...
So then that must mean we're moving
So we have
horizontally.
to set our texture index to 0.
So wall segments x by y dot texture index set to 0. Now, if we were not moving any other direction, not moving horizontally, that leaves one direction.
We better be moving vertically.
Or we have a very interesting direction that we shouldn't be moving. But that would be moving vertically, and we have an index of 1 for vertical.
All right, very cool.
And let's see. One last thing. Actually, I think that does it for setting wall segments. We should be able to run and test now. So build, no errors found. If we run...
Ooh, look at the pretty wall.
The bikes are drawing walls, but the bikes are not centered on the wall. So we'll need to correct that. Also, the bikes can go...
Whoa, look at that fine draw. Oh, it's so fine. No wonder it's so fine. I forgot. There's no wall collisions in. I was like, that was so amazing, but unfortunately, I'm lost.
So we need to take care of collisions, but also before we even bother with collisions, we need to set the appropriate offset, because the bike is offset to the top left. And that makes sense thinking about it. We haven't centered the bike on the line itself, which means it's residing on the top left corner of each individual block. Mm-hmm. We would rather have it be centered on the block. So if we look at draw, right after we get the draw position, if we offset that by half of the grid block size, then we should move to the middle of it. So that way we could take the draw position and increment it by a new vector 2, looking at the grid block size divided by 2.
Right.
So now if we build and run, now our bikes align nicely. We, of course, have the origin back in the game where we have half the width of the texture, and now we're taking into account half the width of a grid block.
Man, look how tight I made that line. Okay, too much fun.
So soon we'll need to take into account collisions.
This reminds me of a, certain screensaver.
Indeed.
With bikes. Okay, so now that we've got that, you ready to go ahead and get the wall collisions put in? And it's pretty simple.
We should put wall collisions in because it is...
So take about 3 seconds to do.
So that's back up here. Well, right before we set the wall, we could do a check before we set it to filled. First, all right, we're on a segment. Is this current segment filled?
Exactly.
So if wall.segments x by y dot filled, if that is indeed the case, we need to call upon the game's collide wall method and have it handle the wall collision. Another case where we would like a collision to occur is if we're out of bounds off the grid. We'll count that as a collision. So that means we could go down to the very end of that overall if statement, drop an else clause, and call upon collide wall again. So that way hitting the edge or hitting a wall should call collide wall. Now at the moment collide wall doesn't actually do anything, so it would probably be a good idea to implement collide wall.
Now stand back. This is some extremely complicated stuff here.
Alright, so get ready for this. Collide wall. We need to affect the game state. We need to affect it by setting it to... Stopped. And that's about it for collide wall.
Yeah. And test time.
So testing, let's see. First thing could be a wall collision. And
I see where an offset would be handy with...
Right, before we erase this now, before we reload the program, looking at the green bike, his wall starts offset from the edge of the screen. So let's take a look at why that's happening. Because the other bike's one works just fine. The green bike, player index 1, is starting at 0. But we update the code before we draw it. Update gets called. Update is in turn going to find move inside of bike. I'm trying to avoid scrolling too much, so I'm kind of abbreviating and skipping over some stuff. But essentially, this happens before drawing happens. Position starts at 0. Direction is set to right, which advances it by 1. It is now 1 off the side of the screen.
Right.
We could counter this by starting it with a negative value.
And it's not going to give us a problem with our array because by the time we get around, it is at 1.
Right before it, actually. So we get in right before the array,
or 0.
we do that very line.
Yeah.
And then we check, and by that time we're in bounds.
Exactly. So now it looks good.
So that cleans that up. I've tested a wall collision, or a edge of screen collision. Let's test a collision with an actual laser. Well, red one works. Just for the sake of testing, let's see who can hit the other one's wall first.
Well, you put pressure on me. I wasn't really holding the control. All right, go again.
All right, see who can hit the other colored wall first. Tink.
Oh, first. Okay.
I shall invert the rules and then I shall win.
Okay, so good deal.
But collisions are working. Now, for further testing purposes, it would be very convenient if we could restart the whole scenario in-game. So let's go down to the stopped state, and let's look for input so that we can restart the entire thing without having to reload the program. So inside of the stopped state, let's get some gamepad input. Let's take our gamepad state. So gamepad state. Let's look at gamepad. Well, I briefly forget how gamepad works. Gamepad.getState. Here I'm just going to hardcode it to 1, since now we're kind of way off the edge of actual gameplay, and this gets into the realm of debugging and testing things. So we'll just look at the player 1's controller, and we'll look for the start button. We'll say if the gamepad states buttons.start is pressed, then we'll allow the game to restart. So let's block this in. First thing we want to do is to make a call to the create scene method. Of course, we'll have to adjust it as well. And after we create the scene, let's change the game state back over to a state of playing. Now, at the moment, that's going to be still very broken because create scene only creates things. It doesn't clear anything.
Right.
So if we manage to end
and then start,
we get a lot of copies of the bike, and the walls don't erase. And upon restarting, we immediately collide.
Yeah.
So you've got a very nice grid of bikes going.
I just thought I'd really make it clear as to what's happening. I am sending my missiles. Oh, you were sending a lot of missiles too.
So, I mean, while this is an entertaining effect, it is very far from the correct effect.
That's right.
So we need to adjust create scene and make it able to clear everything out before it recreates things. So, scrolling back up to create scene, we need to do things like taking the actor list. We need to look at actor, its actors list, and tell that list to clear, so that way we don't get an insane number of bikes. Also, we need to look at the wall. We need to call the wall's reset method, so that the array gets reinitialized and cleared out.
But that makes an interesting scenario pop up.
It does. Very briefly, let me run and test. Cause a crash scenario. If you hit the start button, everything restarts, and it looks like it's working perfectly.
Mm-hmm.
But there's a very slight inefficiency created, and actually there's some unnecessary code based on how it's working now. If we look at wall has a static constructor that calls reset. Game 1, initialize calls create scene, which in turn calls reset, which means that reset is going to get called twice. We could prove that by putting a breakpoint over the segment's initialization line, running the game and seeing one hit.
And that one hit's actually coming from that reset, from the static constructor.
So that's static constructor's out of the way. We run again.
Now
that's coming from the
method callback over in game 1.
In create scene.
So yeah, so as you can see, it's being called twice, which means now we can completely remove the static constructor because there's really no reason for the safety net there.
Right. The safety net was convenient when we had our hard-coded wall. We're not doing that anymore. Create scene is responsible for initializing and resetting the wall. So if we completely remove the static constructor and set a breakpoint, we hit once, we continue, and then we begin playing the game.
Perfect.
So that has the scene restartable. Everything's cleaned up.
That's everything except for smooth movement.
One thing remains, and that's smooth interpolated movement, because the bike movement is still block. It's still block for block exactly what the wall is doing. So let's go back to bike, and let's finish off the movement code. Let's go up to the draw method for bike, and let's drop in between the lines where we define draw position and offset it. So I'm going to drop a few spaces in between those two. And I'm going to start an if block. The goal here is to look at our current position on the screen, and then look at where the next position would be if we moved one. So basically look at our direction and see where the next movement is going to be. and then using the amount of time remaining, interpolate between the two positions to give a smooth interpolation over time instead of over grid block advancement. Now, I need to do a check before I attempt this interpolation, since we need to figure out a relation between the time remaining and the move time, where either of those could potentially be 0, depending on how things are set. We don't want to cause a division by 0 and then feed an invalid result over to the sprite batch, which would result in the entire bike disappearing. So we need to do a check and make sure that we have some time that we can interpolate over. And we'll do that by making sure that the time remaining, so this dot time remaining is greater than 0, and this dot move interval is also greater than 0. Make sure we have some sane amount of time that we can interpolate over. Because if not, what I'll do is I'll simply set the draw position to be exactly equal to the start position. And I'm getting just a fraction of a hair ahead of myself because we're missing some variables. When I go to do the interpolation, I'll have two vector 2's, a start position and an end position. So let me jump back in time a few lines and define both of those. I'll make a vector 2 called start position, and we'll set that to what draw position was equal to. As a matter of fact, I'll completely cut that code and move it to start position, and then simply leave draw position uninitialized. So I have a start position, and that's the appropriate drawn position for the current block. I'll copy and paste that line and change the name to end position, where end position should be the current position plus the direction. So as though we had just moved in the current direction. And I'm going to put that into parentheses to make sure that that part solves first. And then again times block size so we get the appropriate drawn position. So there we have, that's what we're trying to interpolate between start position and end position. Now fast forward to where we've decided that we don't have time to interpolate over, so draw position will be set directly to start position, just where we are currently. Now, if there is time remaining and a move interval, then we want to interpolate between start position and end position. So the first thing we need to do is to come up with a percentage value to drive the interpolation. I'm going to make a float variable called %, and we'll set that equal to the value of 1 minus the float casted result of this time remaining divided by this dot move interval, and that time remaining divided by move interval should give us a value in a range of 0 to 1, but it starts at 1 and moves down to 0 because these should start out being the same value if we have just set time remaining. And time remaining is going to decrement, so this overall value is going to get smaller approaching 0. We can invert that by subtracting 1 from it, because then we would start at 0 and grow to 1.
Right.
And that makes a more logical value to interpolate over.
Right.
So we can perform the actual interpolation and store that result in draw position. So draw position can be equal to vector2 dot lerp, where we will interpolate from the start position to the end position, and the exact point will be given by %, which could have maybe been more appropriately named amount, but close enough.
Yeah, it works for me.
And now we still have our offset. You can see it was important to maintain this grid block centering offset, make sure that that was done after we had decided upon a draw position. But with all that now, let's build and run. And, ooh, look at that. Especially with braking put in. Braking can get nice and slow, but still look smooth, even though behind the scenes, right behind that very graphic, the walls are still popping into place one block at a time. But the sprite for the bike nicely covers all of that and is now being interpolated block by block as it's moving. So very nice looking end result.
Boy, look at those tight turns, man.
So I guess now we'll play out this round before we think.
All right, well, that's it.
Yes, that's it. That is the Laser Bikes engine. We have bikes, walls, smooth movement, the whole 9 yards.
Now, there's a lot of things that they can do with this. First of all, they can go ahead and spin just an extra 15 minutes thinking about collision and get it to where the collision is going to, well, occur if the bike hits the wall, period, meaning like the nose of it. Like right there, you've got half your bike over that wall because,
Yep.
well, think about the code, think about where the collision is actually occurring.
Right, remember that point that was the origin of the bike sprite, right between the bike and the tail, which is about the point that looks like it's colliding. That's because that's the point at which blocks occur.
But there's some rectangle type stuff you can do that could be handy.
The blocks themselves are already given as a rectangle.
Yep. So just some ideas. But yeah, there you go. This is a very simple engine for the most part. We now have 2 bikes cruising around. Be very easy to add 2 more bikes and position one coming in from the top, one coming in from the bottom. Just need 2 more controllers, which I don't have here in front of me, but then you'd have players 3 and 4, and boy, that'll get messy quickly. Now, I would be very interested in seeing some students take this and run with it and come up with some really fun things, add power-ups, maybe even some sort of power-up that provides you with a momentary weapon that will allow you to knock holes in a wall or something, or make the wall fade out behind you or at the very end, and slowly, as you're cruising along forward, it's kind of following behind, fading out. So the screen doesn't get as jumbled down as this. There's a lot of different things you guys can come up with, but I'd be very interested to see what students could do with this game. And with that, that wraps up Laser Bikes. Thanks a lot, everyone.